derived equivalence so singularities on the pre-image of W inverse of 0 in X. So that will be equivalent to dB sing pre-image of W inverse of 0 in Y. Okay, so if I have a function on the base, then I can consider two compositions. And so if the derived categories of the original varieties were equivalent, then the singular categories of the zero fibers are also equivalent. Now this isn't, for smooth varieties, this is not too hard. You would basically already have a functor that moves sheaves to sheaves, and you would have to say that sheaves supported on one zero fiber would have to map to sheaves supported on another zero fiber, and then projective complexes can be mapped to projective complexes. It somehow, once you start talking about orbifolds, it somehow gets more difficult because of, in our case, we want to be able to work with non-compact Z. And so for varieties, you can compactify morphisms, while for general orbifolds, this result it's a technical result which isn't quite proved in generality. So you have to really look at this particular situation and show that it makes sense. Right, so okay, so that really gives a geometric interpretation of the original result of Orlov, and what's sitting behind is that, so if you mod out this space by Zn plus 1 in the sense of orbifolds, then both of them become resolutions of the same singular affine variety. You apply Mackay correspondence and get derived equivalence without taking into account W's. And then you can plug in W by our result here. So you can add it in, and categories are still equivalent. All right, so now what is the generalization to the toric case? Wise to toric case. Well, so what are toric varieties? For purposes of this exposition, okay, so let's say we have T, which is algebraic torus, and then there is sigma, which is a fan, some combinatorial data in N tensor R over Z, and N will be algebraic homomorphisms from C star to T. It's really just a lattice Z to the N. And if you haven't seen these toric varieties and description of them, you can skip this thing, not worry about them. And then a toric variety can be, one of the ways of looking at it is you take a flat space of a certain dimension that will specify, you throw away some subset, and then you mod out by a group. This is a description that generalizes definition of a projective space. Usual projective spaces, Cn plus 1 without origin modulo C star. It turns out that for toric varieties, you can do that, and let me just write for those familiar with what fans are. So P is the number of one-dimensional cones in the fan sigma. B is a union of some coordinate subspaces, linear subspaces in CP of codimension greater or equal to 2. And then G will be a certain group, which is, in the case of P being smooth and projective, in this case it's homomorphisms from Picard group of P into C star, which you also can represent as C star to the P minus n. So this picture exists in arbitrary case. So in general, G is isomorphic to C star to some power times a finite abelian group. And this construction is called Cox-Butterworth construction. It is very nice because in the case of what is called quasi-smooth toric varieties, when you have finite quotient singularities, this construction is completely canonical. You just do it starting from the fan. And so you can use it to define a toric variety, but if G has finite stabilizers, you actually can define it as an orbifold. So there's a canonical orbifold structure in the case of quasi-smooth toric varieties, just from Butterworth's construction, Cox and Butterworth construction. All right, so now G acts on CP with weights alpha 1 and alpha p. So in the case of projective space, we just have C star and it's acting on Cn plus 1 with weights which are all equal to 1. Now, to get the top, so the canonical bundle of the toric variety. So in this case, toric variety is n-dimensional, and so the torus that we're acting sort of has dimension n less. So the quotient is n-dimensional. So one needs to consider the quotient. Again, we start with the same space. And for these purposes, it's irrelevant what B is. And then you multiply by C, and then you multiply by G, and you say where G acts on this extra copy of C by weight, which is minus alpha 1 plus alpha p. So this is a standard result about canonical class of a toric variety. It's equal to minus the sum of the torus invariant divisors. It's for projective space, all these numbers are equal to 1, and this becomes minus n minus 1. In general, it should be understood that this is several copies of C, and these guys are vector valued integers. All right, so okay, so we have omega np, which is Cp without B times C mod G. And as before, it maps onto the quotient in the naive sense. So this is the quotient that you're getting if you're trying to compute just the spectrum of the algebra of invariance. This will be a fine variety. But because I want to use Mackay correspondence, I need to know that this map is proper, which isn't always the case. So for Fano surface, for Hirzebruch surface F3, there is a -3 rational curve. And it turns out that the restriction of this bundle to the -3 curve collapses to 0. So the fiber is not proper. I want the situation when the fiber is proper, so I want to assume that P is final. But later I might have time to explain what would I want to do without this.
So that means your fiber was stable.
Sorry? Yeah.
And the global section is anti.
Yeah. So this is also spectrum of H0 of omega and P O. So just regular functions, right? So what would be standing here? So let me just write it first in quotation marks. I'm taking the space CP, and I'm modding it out in quotation marks by a certain subgroup of G, which I will call GK. So let me just define GK, and then we consider examples which explain why I'm writing quotation marks. So GK, by definition, will be the kernel of the map from G to C star, which is the homomorphism defined by minus alpha 1 plus alpha p. So this is, in the case of projective space, this will be just taking the n plus first degree up to inverse. Right, so what happens is that this is a smaller group than G. It will be acting on a space, so what I'm trying to use is CP in quotation marks, GK. I'm trying to use the fact that, again, this should be equal to the quotient of CP by C star mod the original G. So it's a starting point of geometric invariant theory that whenever you're taking quotients, you either have to pass to algebra of invariance, which is somewhat of a crude thing, doesn't separate all orbits necessarily. But if you want a better concept of a quotient, you have to throw some points out. You have to throw some bad points out. In this case, the bad points will correspond to this set B, which I haven't defined, but it's a part of a general construction. And then the quotient becomes reasonable. Here, I'm saying we can throw out a different set of points. We can throw out 0 on this side. So I'm inserting B back, but I'm throwing out 0 on this side. However, this is not enough. That's why I'm writing quotation marks. So for general Fano varieties, 0 point here will still have large stabilizer, which is not finite. So we need to throw more to make sure that this quotient is nice and exists. But this is not, we'll see that there are choices to do that. So it's, we cannot do it uniquely. And so in that case, assuming that you can define this quotient, really the same argument as before gives a theorem that so if you have, if Y is the Z of W, and W is the section of the anti-canonical bundle on the toric variety, on a Fano toric variety. So P Fano projective smooth and toric. So then dB of Y will be is equivalent to the singular derived category of the 0 set of the composition, where we take this quotient CP mod GK, and then we go to our affine variety Z, and then we apply, well, essentially this W really. It can be identified with the function on Z. Now, and again, there is a slight issue of grading here that I'm sort of ignoring, which, so we'll see now in examples. So the proof is really the same, because what happens is whenever I can make sense of this quotient will automatically be birational to the canonical bundle of P. And if I know Mackay correspondence equivalence between derived categories, then I just apply the statement that was quoted earlier. If you have derived equivalence without W's, then you also have equivalence with W's. So that's so the only issue is actually to understand what this thing is. And so for that, let's look at examples. So example 0, when P is equal to Pn. Then we have G is equal to C star. And what is GK? So we have a homomorphism. T goes to T minus n minus 1. And GK is its kernel. So this is Zn plus 1. And so this is GK. So the GK by definition was the kernel of the homomorphism that corresponds to the weight of the canonical class. And then the quotient Cn plus 1 mod Zn plus 1, this thing makes sense as orbifold. So that in that sense we can write this quotient. So we are really just back, this construction extends the setting of our original setting of Orlov. And by the way, I want to say that original result of Orlov also works for weighted projective spaces whenever hypersurface is quasi-smooth. So in that, but you only interpret all of those as categories of orbifolds. So you won't take covariant bundles. So example 1, really the first interesting, when x is equal to F1, which is by definition projectivization of the bundle O plus O of 1. And these are bundles on P1. So this is a rank 2 bundle on P1. When you projectivize it, you get a surface, and it has the Fano condition, so it's Delpezzo surface. So this case is nice because GK is reasonable in this sense. Okay, so let me just write. So it's equal to C4 without B, whatever it is, by the group which is actually equal to C star squared. Now, what is the so weights of C star squared on C4? So they're given by 1, 0, 1, 0, 0, 1, and then minus 1, 1. Okay, so now what is GK? It's a subgroup in C star squared, which is formed by pairs of complex numbers such that psi C squared is equal to 1. Where I'm getting this, I'm trying really to sum up along the rows and then negating. I'm getting the weight of the canonical class. So this is alpha 1, alpha 4, and the weight of minus their sum. So you sum them up, you get 1 and 2, and you have minus 1 and minus 2. So this goes to the first degree, this goes to the second degree. Well, what is this? It really means that psi can be recovered from zeta as minus zeta minus squared. So this whole group is equal to C star. So now weights of GK on C4. So really, I'm restricting these weights to this particular subgroup. And if you just do the calculation, you say that it's -2, -2, 1, and 3. So we're looking at the following situation. We have C star action on C4 with these weights. How can we take a quotient, except in the naive sense of spectrum invariance? Well, we have to throw something out. So, and what we're throwing out is not unique. Definitely we need to throw out 0 because it has a huge stabilizer. But you have to throw out different things. So we can throw out the set Z1 where, well, with C4, let's assume coordinates are x, y, u, and v. So we can throw out the set where x and y are both equal to 0. And then we look at C4 without Z1 and then mod out by C star. If we look at, we can also throw out points where u and v are equal to 0. And then we look at C4 without Z2 mod C star. So there are two different ways, and there is no really decent way to combine them. You have to choose one or the other. There are two things that can stand on the other side of this generalization. And I guess a very old result by Miles-Reed is that if you try to see, so these things are birational because you can throw out both of them, mod out, and this is a common open piece. If you try to see how they're different, an old result by Miles-Reed, I'm told something almost like his thesis, implies that this is what is later is called a flip. So these numbers tell that this is a flip. Right? So you basically, it's some birational transformation that throws away one rational curve and inserts another rational curve with different data. Okay, so the last example would be case of P1 by P1, which is a little less pleasant than F1 because GK has torsion. So X is equal to P1 by P1. You have still, and obviously this is C4 without something, mod C star by C star. We just take the product of the usual construction for P1. Now weight of action of C star by C star on C4 are also obvious. You have 1, 1, 0, 0, 0, 0, 1, 1. Weights for canonical class would be -2, -2. And now, because of that, GK can be defined as pairs of sine zeta such that sine squared zeta squared is equal to 1. Now, this group isn't C star. It's actually, because this condition tells you that sine is equal to plus minus zeta inverse. And there is no decent way of choosing plus or minus. So this is isomorphic to C star times Z2. And C star is where zeta lives, and Z2 is where plus minus lives. And now GK acts on C4 by the following thing. So you have zeta inverse, plus minus zeta, plus minus zeta. So if we try to, let's say, forget about Z2, so then it will be just C star action, and then the weights will be -1, -1, 0, sorry, 1 and 1. And it's the same situation if you have x, y, u, and v. If you're trying to take a quotient, you have to make a choice. You have to, well, it's the same really formula, just a slightly different action. You would have to Either throw out the Z1 that's written on that board, or you throw out Z2, which is written on the board, and then you take a quotient by C star. Well, actually not C star, but Z2 doesn't really affect the choices much. I still have orbifold. I still have a smooth orbifold. And in this case, these weights mean that the difference between two ways to take the quotient is what is known as a flop. So there is this birational transformation called flips and flops, and there is difference between those. In both cases, you're throwing out a rational curve and inserting something else, but just look at how this rational curve behaves with respect to canonical class. So it's just a normal bundle is what makes the difference. Right. So again, there are two ways of taking the quotient. Both of them will actually work for our generalization, and that's of course based on the statement which is, well, in general it's conjectural still, but in this case it's easy to check it, that if you have two birational Calabi-Yaus, then derived categories are the same. And this is also going back to the early minutes of this talk. So this is an example when derived categories are the same, cohomology groups are the same, cohomology rings are different. So from the derived category you can recover, using Hochschild homology, you can recover cohomology space, but not the canonical ring product. Because, and what should give you the ring product is another interesting conjecture. So this is related to this work of Tom Bridgeland on stability conditions on derived categories. So supposedly, if you have some additional structure in the derived category, you should be able to get some sort of product. So let's stop here.